I'm Dr. Fred DePiro, and this video is about analysis by equivalent circuits. We'll learn how to find voltages and currents for all the elements in a circuit using this technique. Prereqs include Ohm's law, passive sign convention, identifying nodes and meshes, and the ability to form series and parallel combinations. Now, this is a nice method. That's why it's of interest. It's easy and it uses simple calculations. It is an ad hoc method, however. It's not systematic. The specific steps that you'll need to take will vary depending on the circuit. You'll see that as we go through some examples here. Nevertheless, it still might be attractive to you because it involves simple calculations at each step. The overall approach is this. We simplify a circuit by series parallel combinations until only a single resistor remains. Then we use Ohm's law to find the voltage and current for that resistor, then work backwards, undoing the simplifications to reveal the voltage and current for all the resistors. So before we get started, let's discuss what happens when we simplify a series combination. Let's look at the circuit conditions before and after that simplification. So here you see a 3 and a 2 ohm resistor being simplified to this 5 ohm resistor. In each case, this voltage source sees 5 ohms. The circuits are equivalent. The total resistance seen by the source is the same. That means that the conditions for the source are unchanged. The current through the source remains constant. That also implies that the current through the 5 ohm resistor is the same as the current through each of these in the original series combination. So if we go from the simplified version of the circuit back to the original, we know that the current that we have through this R equivalent is the same as the current through the original resistors that resulted in that series combo. This demonstrates how to first simplify a circuit and then undo that simplification to learn about the original version. Okay, let's take a look at the parallel case. Here we have two 8s. We're going to simplify those to an R equivalent of 4 ohms. Let's talk about the conditions before and after that simplification. Here the circuit's driven by a 3 amp current source. Now, the voltage across that current source, Vs, is determined by the total resistance that the current source has to drive. These two circuits are equivalent. 2 8s make a 4. Therefore, the total resistance seen by the source, the current source, in each case doesn't change. Hence, the source's voltage is unchanged. And this source voltage here and here is the same as A and B, and that's also the same as this other voltage, V4. So, if we have the simplified version here, if we know its voltage, V4, and we know that it came from a parallel combination, then we know the voltages VA and VB to be exactly the same as V4. So here's our technique. Once again, simplify by series and parallel combos until we have just a single resistor. Use Ohm's law to find the voltage and current for that resistor. Then work backwards, undoing the simplifications to reveal voltage and current for all the resistors in the circuit. Okay, we'll start off here. There's only one simplification we can do. It's these two 10s in parallel. And I'll just take the opportunity to point out that this 2 ohm is not in series with either of the 10 ohm resistors. They do share a node A, but the 2 and this 10, for example, do not share node A exclusively. This other resistor also taps into it. Okay? So we don't have a series combo here. We just have the two 10s in parallel. Two tens make a 5. Now we want to locate that R equivalent at the location of one of the originals. So I put it here on the right. We replace the other location with an open circuit or break. This is because the originals were in parallel. Now in general, as you're going through this and simplifying, there may be multiple options that you can take doing a series and parallel combination. That's the ad hoc nature of this technique. In this case, we only had one option before, we only have one option now, but in general you can have more than one. Okay, so in this case, we are looking at a 2 and 5 in series. We're going to combine those to get the equivalent. Then we're going to redraw, and when we redraw the equivalent, we'll put REQ at the location of one of the originals. Putting REQ here, making it this resistor now 7 ohms, we then replace the other location with a wire. That's because they were in series. Well, we're down to one resistor and one source, so we can use Ohm's law to find out what's going on with this 7 ohm resistor. It's in parallel with the 14 volt source, therefore we know V7. We know it to be equal to 14 volts. We also know the polarity, plus sign up. We can then compute I7 downward, that's as involving passive sign convention, and I7 is just going to be 14 over 7, or 2 amps. Now we're going to work backwards, so thinking caps on. We're going to undo that series combo. We know the current I7, it was 2 amps. The 7 ohm resistor resulted from a series combination. Therefore, we know the current through those. The current through the 2 ohm and the current through the 5 ohm is also 2 amps. Now we can use Ohm's law to get the voltage across those two resistors, 4 and 10. And now we'll undo the combination that resulted in this 5 ohm. The 5 ohm resulted from the combination of the two 10s. We know the voltage across the 5 ohm resistor. Therefore, we know the voltage across the two 10 ohms. They're all 10 volts in this case. Now that we have the voltage across those two 10 ohm resistors, we can compute the current through them, each 1 amp. You'll notice, by the way, the 2 amps through the source and through the 2 ohms split evenly. That even split is due to the fact that these two resistors are equal valued. All right. So we went through this process of analysis by equivalent circuits. First thing we did was to simplify by series and parallel combos until a single resistor remained. We found the voltage and current for that resistor. Then we worked backwards, undoing the simplification step by step to reveal the voltage and current for each of the resistors in the circuit. It's a pretty nice technique. It will reveal all the voltages and currents. It's easy to do. The calculations are simple. Only thing is, this is an ad hoc method. I can't tell you ahead of time exactly the sequence of series parallel combos. I can't even tell you if the circuit can be reduced by series parallel combos. In some cases, it cannot. Okay? But for simpler circuits, this method works well.